This video is on precipitation reactions and net ionic equations. So this is going to be a very specific type of one of the double replacement reactions. So of all the ones we've talked about so far, this is focusing in on specifically double replacements. What does it really mean when a compound is aqueous? Okay, so whenever you see AQ after a compound, what does that mean? Well, first of all, it means that it's dissolved in water. And when you dissolve these things in water, they don't really exist like a compound anymore. They don't stay together as a unit. So for instance, if you take sodium chloride table salt and you put that in water, yeah, you don't see the actual physical salt anymore unless you saturate the water. But you put a couple of crystals in a big glass, okay, that's going to dissolve. Well, when it dissolves, it doesn't stay like this anymore. Its aqueous form is actually its ions. Okay, so when you put something like table salt into water, what this is really saying is that the water has sodium ions in it and chloride ions in it. Okay, the compound really exists as ions if you dissolve it in water. Okay, that's what it means. So if you see aqueous, you're actually using ions. It does not exist as NaCl, but rather as sodium ions and chloride ions. Types of reactions in aqueous solutions. So what we're going to talk about today is the formation of precipitates. The next unit is going to include formation of water. We don't get too much into formation of gas. It only happens every once in a while. But the next unit on acids and bases, neutralization reactions, that's where we're going to see double replacements forming water. But today is strictly looking at precipitates. Okay, so the definition of this, and you've seen these before, but just to have a solid definition for you, a solid formed by the addition of two solutions. Okay, so you've got two different solutions. Drawing this out here so we can physically see an example. Okay. All right. Each of them has ions in it, positive and negative ions in it. They are dissolved. They are aqueous. You can't see them. You pour these two together, or pour this one into that one, however you want to do it. What ends up happening is that some of these positively or negatively charged ions are going to actually bond with the positive or negatively charged ions in this solution. And instead of ending up with just nothing but ions, all aqueous ions, some of them actually turn into solids. So these always form as the result of a double replacement reaction. So here's my example down below. This is a solution of silver nitrate, AgNO3. Okay, so we could say that this beaker has the AgNO3 in it, where the positive ions are the silver and the nitrate ions are the negative ions here. And we'd pour that into a beaker full of sodium chloride. And in this instance, the sodium is the positive ion and the chloride is the negative ion. You pour those two together, you'd end up, well, you originally think you'd end up with one beaker full of four different ions, right? Sodium ions, chloride ions, silver ions, nitrate ions. You'd think you'd have four different ions, but what ends up happening is you form a solid salt out of this. When silver ions and chloride ions come together, they form a solid. So what you'd end up getting out of this when you do it is you'd have a solid forming inside of this solution over here. It'd be little white crystals. Silver chloride are white colored crystals. Okay, that would form in this solution. If you let it set, at first it would look kind of cloudy, but if you let it set for a minute, all of that salt would go down to the bottom of that solution and you could clearly see it. Well, what happens to the sodium and the nitrate ions? They are left in solution. They're still aqueous, so they're still floating around in here. The sodium ions are positive, the nitrate ions are negative. These crystals down here, though, are made out of silver and chloride ions. Okay, so what we like to do in chemistry is to simplify things if possible. So we have something called a net ionic equation. So this is the example we'll work with here for a minute. This is sodium hydroxide plus, this is copper 2 chloride, CuCl2. Okay, these are both aqueous in solution. You react those by pouring them together. You end up with sodium chloride, table salt, that's still aqueous, and copper 2 hydroxide, which turns into a solid. Well, you got to remember that ionic compounds exist as ions in solution. So what's really going on here? Well, you have sodium ions, you have hydroxide ions, you've got copper 2 ions, right, plus 2 on the charge there. You've got chloride ions, okay? All of those things are aqueous. They are all aqueous in solution. And on the right-hand side of the equation, the product side, the sodium chloride is aqueous. Okay, so the sodium ions plus the chloride ions. This guy right here, though, the copper 2 hydroxide, it is not aqueous. We can't break it into ions because it's a solid. Okay, so that one remains a solid. What we have written here is called a complete ionic equation. So this whole darn thing is called the complete ionic equation. It's very long, it's very lengthy. We show every ion involved in this reaction. Okay, so if you're asked to write out a complete ionic equation, break apart all of anything that says aqueous into its ions. Okay, break it apart into its ions. And be careful, right? This one, Cl2, is actually 2 chloride ions, right? 2 sodium ions, 2 chloride ions over there. So just be careful when you're breaking those things apart. So that is called a complete ionic equation. Well, we start to pay close attention to what's going on here, and we might notice something. We can notice that the sodium ions and the chloride ions are on both sides of the equation. We have them on both sides of the arrow, okay, arrow being right here. These are called spectator ions. Why are they called spectator ions? Well, because you have the same ion here as you do over here. You have 2 of them here, you have 2 of them here. They're both aqueous, they're both dissolved in water. They haven't done anything in this reaction. They started in solution, they stayed in solution. You haven't done anything to the sodium ions. Same thing with the chloride. It was aqueous to begin with. There were 2 of them. 2 of them over here that are aqueous on the right-hand side. So those are called spectator ions. They do not participate in the reaction. So what we would like to do is to remove them. All right? It's just clogging up space. It's taking up a whole bunch of this line here. So what we're going to do is take all of the spectator ions and remove them from this equation. And it's going to clean it up nicely, because the only thing that's actually reacting are copper 2 ions, hydroxide ions. Those are the only 2 things reacting, and copper 2 hydroxide is the only product that's actually formed. So we've removed all the spectator ions from this reaction. When you do that, you get something called a net ionic equation. So all you have to do is just write whatever's left. What's left? 2 hydroxide ions plus a copper 2 ion, this one plus this one, okay, yields CuOH2. So we form the CuOH2 over here. So the net ionic equation, the whole thing, 2OH negative, 2 hydroxide ions plus 1 copper 2 ion yields copper 2 hydroxide. This is the net ionic equation. This is what we want out of this mess up here. Okay, so how do we know which precipitate forms? For instance, how did we know, in this last one, that the sodium chloride was going to be aqueous and the copper 2 hydroxide was a solid? Okay, so I'm not just guessing as to which one that is. I have some information. I have a set of rules that's going to help me. Okay, a set of rules that's going to help me determine which things are aqueous and which things will be solid. Sometimes when you do this, you could actually end up forming nothing but aqueous solutions. Well, if that's the case, nothing has reacted at all and you get no reaction. Okay, so if you end up trying to form a precipitate, but you check both the products and both of them are soluble, both of them dissolved in water, then that means that you have no reaction happening. So you'll be given a list of the solubility rules. Okay, you should keep that, or you already have one of the 2. To determine a precipitate, you check the possible products against the rules. Okay, so you're going to go against all the rules there, see what you're going to form. So let's just take a look at our example here and show you how I knew which thing was actually going to form. Alright, well, we know this is a double replacement reaction. We know the sodium and the copper are going to switch places if something's going to happen, right? Okay, they're all aqueous. We know our possible products here are aqueous sodium chloride, okay, and, well, actually, we don't know the aqueous part yet. I'll go ahead and erase that. Whoops, one too many. Sodium chloride plus copper 2 hydroxide. Okay, so let's say we don't know their states yet. What are you going to do? Well, check the solubility rules, okay, for the first one, sodium chloride. All right. Rule number 1 on your list there applies to lithium ions, sodium ions, potassium ions, and ammonium ions. The statement says group 1A and ammonium compounds are soluble. Okay. Well, if something is soluble, that means it dissolves in water. There are 0 exceptions to that. So anything with a 1A or an ammonium ion in it is going to be soluble. This one right here has sodium. Sodium is a 1A metal. Okay, it is soluble, meaning it dissolves. Soluble means it dissolves in water every time without fail. And if you check Rule 3, it says most chlorides, bromides, and iodides are soluble. Okay, and that's what we're looking at down here. Okay, most chlorides, bromides, and iodides are soluble. Well, this is a chloride. And if you check the table there, there is a list of exceptions, but none of those exceptions are sodium chloride, NaCl. Okay, therefore, it's not an exception to that rule, and rule number 1 would tell you it was soluble anyway. Okay, so that one is definitely going to be aqueous. If we look at the next one, CuOH2, okay, you'll note that there are no rules applying to copper ions. Okay, so if you look down there on the left-hand side, rules 1 through 7 are not going to apply at all to copper. Even rule 8 doesn't apply to copper. We have no rules for copper ions, which means we need to look at what it's bonded to. We need to look at the hydroxide ion. Okay, and so rule 8 applies to hydroxides. It says most hydroxides are insoluble. Most hydroxides are insoluble. And what does that mean? Well, that means it's not going to dissolve. Most hydroxides will not dissolve in water. Well, take a look on the right-hand column for exceptions. It says 1A hydroxide, so if it was something like sodium hydroxide, hey, look at that, that's right there, that would be soluble. If it was calcium hydroxide, strontium hydroxide, barium hydroxide, or ammonium hydroxide, those are the hydroxides that actually do dissolve in water. This is not on that exception list. Okay, CuOH2 is not an exception to Rule 8, therefore copper 2 hydroxide is insoluble. Okay, it is the precipitate. It's going to be the solid. If something is insoluble, it is your precipitate. Okay, one more thing to show you, and I kind of already mentioned this, but I want to show you what happens if you end up with, say, a reaction that's not, in fact, actually going to do anything. So let's say I have the following situation. And you're asked to predict what's going to happen here. Well, okay, you'd say the only thing that could form, I could have lithium chloride, which is aqueous, or I could have sodium nitrate, NaNO3, okay, which could be aqueous. And we can check this. In fact, if you go straight to rule number 1 for both of these, anytime you have a 1A metal ion, that's going to be soluble. So lithium ions are soluble in solution, no matter what they're bonded to, so that's going to be soluble. Sodium nitrate. Sodium is a 1A metal. That's going to be soluble. And in fact, if you check down on Rule 2, acetates and nitrates are always soluble, no exceptions. So that is always going to dissolve. This one is always going to dissolve. Well, what's happened here? You took a beaker full of lithium ions and nitrate ions, okay, and you added that to a beaker full of sodium ions and chloride ions, and nothing happened. You poured this one into this one, and you had exactly nothing form. Everything stayed as ions. Everything stayed dissolved in water. So really what happens when you've got this kind of situation, all right, since you don't form a product at all and nothing reacted, you have no reaction. So that is a possibility. So just be aware that you could do this and find out you never formed a precipitate. Okay? And as far as I'm aware, I've never come across one that has formed two precipitates. I've only seen it work where you form one. So you should have, if it's going to form a product, a solid, you should only get one. And if it doesn't, you do not have a reaction.